Hey guys. So in this video, I want to talk a little bit about logarithmic differentiation. It's a great tool for differentiating when we have repeated applications of the product rule, annoying applications of the quotient rule, or if I have a function to another function. So to start out, I kind of want to go over the logarithmic and exponential derivatives to make sure we're kind of on the same page. So let a be some real number, then the derivative of log base a to the x is going to be 1 over x ln of a. It's all in the denominator there. Um, and so that means that the derivative of ln x, remember that ln x is just log base e of x. So applying the rule above, I have 1 over x ln e. But ln e is just 1, so that tells me that my derivative of ln x is just 1 over x. Okay, next the derivative of a to the x, where a is just some number, is going to be ln of a times a to the x. Okay, applying what we have above, the derivative of e to the x is going to be ln of e times e to the x. But ln of e is just 1, so that means that the derivative of e to the x is just e to the x. And that's kind of a nice property that e to the x has, is that its derivative is exactly equal to itself. So another thing I wanted to kind of talk about is what happens when we're using the chain rule on these. Okay, so I kind of cleaned things up here, and so we're going to let u be a function of x, u equals u of x. And so applying the chain rule here for log base a of u, I'm going to have 1 over ln a times u, right, because that's what's in the argument, and then I need to take the derivative of u. We'll call it u prime. So the derivative of log base a of u is u prime over ln of a times u. Okay, that means that the derivative of ln u is going to be u prime over u. Okay, the derivative of a to the u is going to be ln of a times a to the u times u prime. So cleaning it up a bit here, I have ln a u prime a to the u. Okay. And then the derivative of e to the u is going to be e to the u times u prime. So it's u prime e to the u. Okay. So these are the facts that are going to help us to use logarithmic differentiation as a tool to differentiate some special functions. So next we'll take a look at those. Okay, so we're going to consider a function like this, y equals x plus 5 to the sine x. So I can't differentiate this using product rule or quotient rule or power rule or anything like that. There's really nothing I can use here to differentiate this. But what I can do is I can use the rules of logarithms to help me kind of make this into something I can differentiate. So the first thing I'm going to do is I'm going to take ln of both sides. Okay. So next, I'm going to recall that we have this rule. So ln of a to the b is equal to b ln a. So that power can just come down outside the ln. So I have ln of y is equal to sine x times ln of x plus 5. Cool. Now this looks like something that I can differentiate implicitly. So what I'll do is I remember to treat y as a function of x, and I'm going to take the derivative of both sides. So I have d by dx of ln y is equal to d by dx of sine x times ln of x plus 5. So on the left-hand side, I'm going to have, this is an implicit differentiation, y is a function of x. So I'll look at this formula here. If I have the derivative of ln of a function, it's the derivative of the function over the function itself. So applying that here, I have that this is going to be y prime over y. And then for my right-hand side, I can use product rule. So the derivative of sine x will be cosine x times ln of x plus 5 plus sine x times the derivative of x plus 5, or sorry, the derivative of ln of x plus 5, which is similarly going to be x plus 5 in the denominator, right, using this formula here. And then on top, it's going to be the derivative of that, so which is just going to be 1. So this tells me that, I'll move this up here. So this tells me that I'm going to have y prime over y is equal to cosine of x times ln of x plus 5 plus sine x over x plus 5. Now what I can do is I can multiply both sides by y. So multiply both sides by y here. And that gives me y prime is equal to cosine x ln x plus 5 plus sine x over x plus 5. And then the question now is, what is y? Well, y is my original thing here. So y is actually equal to x plus 5 sine x. Cool. So that gives me y prime, which is my derivative. And so this is how we can use implicit differentiation on a function like this. Okay, so one more case here, y equals tan x to the cosine squared x. So we're going to apply the same process here. We're going to consider ln of both sides, so ln y equals ln of tan x to the cosine squared x. So like before, I can just bring that power down out front. So I have cosine squared x times ln of tan x. Okay, now I can differentiate both sides and get that y prime over y is equal to, by product rule on the right-hand side, I get 2 cosine x times minus sine x times ln tan x plus cosine squared x times, right, because I have a function in my ln, I leave the function as it is on the bottom, tan x, and then I take the derivative of tan x here. So it's going to be secant squared x. Okay, so up here, I have y prime over y is equal to negative 2 cos x sine x ln of tan x plus, so this cosine squared and this secant squared will cancel out. And so I'll get 1 over tan x, because secant squared is 1 over cosine squared. So now again, I can just multiply both sides by y, and I get that this is negative 2 cos x sine x ln tan x plus 1 over tangent x is cotangent x. So I can just write it like that. And then I multiply both sides by y. Well, my original y here is tan x to the, ooh, I'm running out of space. Let me move this down here. I have some space. Tan x to the cosine squared x. And that would be my final answer there. Yeah. Okay, so now that we've considered two specific instances of this kind of differentiation, we call it logarithmic differentiation, I wanted to look at a more general case. So suppose I have y is equal to f of x to the g of x. So this is the same kind of function that we've been, same like class of functions that we've been looking at for the past two examples. We have a function raised to a function. So in order to differentiate this, I would consider doing the same process, right? I would take ln of both sides, so I would have ln y equals ln f of x to the g of x, and then I can move that g of x to the front, so I'll have ln y g of x times ln of f of x, and then differentiating both sides, I get y prime over y is equal to g prime of x times ln of f of x plus g of x times, right, I use the ln of a function, so I leave the function in the bottom, and then I put its derivative on top, and then I multiply by both sides, and I multiply both sides by y, sorry, and I get y prime is equal to g prime of x ln f of x plus g of x times f prime of x over f of x all times y. And then I remember that y is equal to f of x over g of x. So I finally get that the derivative with respect to x of f of x to the g of x, because remember that's y, the derivative of y, is equal to g prime of x times ln of f of x plus g of x f prime of x over f of x times f of x to the g of x. And this is the general case, but it kind of highlights what steps we're going through for any of these problems, right? So the first thing I did was take the ln of both sides. Then the next thing I did was apply my log rules to simplify. Then here I took the derivative, d by dx, and that gave me y prime over y. Implicitly on the left-hand side, fine, it's normal on the right-hand side. And then I multiplied both sides by y, and then I plugged everything back in for y. And this is how, in general, you would solve one of these problems. So we're going to look at some other cases where logarithmic differentiation is useful. So next we're going to consider a function like this. Y equals this huge product of a bunch of different factors. If I was to do product rule on this, as I would think to do first, I would be stuck with 4 product rule steps. And at what point does that get like too much to manage? So I think that a better option for this one would be to try and use logarithmic differentiation. And here's why. So if I take ln of both sides, ln of y equals ln of all of this mess, x plus 2 to the 8th, x plus 3 to the 5th, x minus 12 to the 23rd, x plus 1 cubed. So I can use some log rules here to make this simpler. So I remember that ln of a times b is equal to ln of a plus ln of b. And the other thing I remember here is that ln of, let's say, c to the d is equal to d ln c, right? I just popped that exponent out front. So let's apply that to this here. So I'll apply that first rule to this step here. So I'll have that ln of y is equal to ln of x plus 2 to the 8th plus ln of x plus 3 to the 5th plus ln of x minus 12 to the 23rd plus ln of x plus 1 to the 3rd. So I was just able to split that product up into a sum of natural logs. So next I'll apply that second rule to this step. So I can have that ln of y equals 8 ln x plus 2 plus 5 ln x plus 3 plus 23 ln x minus 12 plus 3 ln x plus 1. Cool. So now this looks like something on the right-hand side that I can differentiate very easily. It's a sum of easy to differentiate functions. So I'll go ahead and do that here now. I'll differentiate. So differentiating the left-hand side gives me y prime over y as before. And then I just take my derivatives down the line. So I have 8 times, this is going to be, I leave the function at the bottom, so x plus 2, the derivative of x plus 2 is 1, plus 5 times x plus 3, the derivative of x plus 3 is 1, plus 23 times 1 over x minus 12, plus 3 times 1 over x plus 1. Okay, so now I just multiply both sides by y, and I get that y prime is equal to 8 x plus 2 plus, or here, let me, plus 5 over x plus 3 plus 23 over x minus 12 plus 3 over x plus 1 all times y, which y originally was this guy here, so I'm lazy, so I'm just going to kind of copy paste this, but you would literally just put y here, and then that would be our final answer. And so rather than applying product rule, 4 times and then using, chain rule and everything else, power rule, all that, I can just use logarithmic differentiation, and I end up just taking a bunch of smaller, easy derivatives of logarithmic functions. So next we're going to look at another case where we have to do a bunch of quotient rule and how that would make this simpler. Okay, so we're going to look at this function here. And just looking at it, if I was asked to differentiate this, I would think this is a nightmare, right? Using just product and quotient rule and chain rule and power rule, this looks like a nightmare. This would be like 50 steps. I just don't want to do it, right? So let's try using our logarithmic differentiation trick. So I'll take ln of both sides of x minus 23 to the 5th sine 3x over x plus 3 x minus 5. Okay, so a couple of log rules to remember. Like before, we had ln of ab is equal to ln of a plus ln of b. We have that ln of c to the d is equal to d ln c. And we also have that ln of, let's say, I don't know, f over g is equal to ln f minus ln g. So if I have a quotient in the ln, I can make it a subtraction of ln's. So let's apply that to this here. So ln of y equals, I'm going to have ln of x minus 23 to the 5th sine 3x minus ln of x plus 3 times x minus 5. So right where that, division is, I just made it into a subtraction of natural logs. And then next, I'm going to break apart these products. So I have ln y equals ln of x minus 23 to the 5th plus ln of sine 3x minus, the important thing to see here is that this is minus all of this in parentheses, ln x plus 3 plus ln x minus 5. Because both of these were in the denominator, so they're both being subtracted from this first sum. So I actually have, let me simplify this here, that. Okay, so the next thing I can do is I've got a bunch of easy, I've got the sum of a bunch of easy log derivatives, so I'll just take the derivative on both sides. On the left-hand side, as always, I get y prime over y. Taking the derivative of this first guy, I have whatever is in the, whatever's in here goes in the denominator as is. So I have x minus 23. Oh, there's a step I can do first here. Sorry. So this guy here can be simplified a little bit further. I can realize that this is 5 ln x minus 23. So I can use that. So y prime over y, as before, is equal to 5 times whatever is in the ln stays there in the denominator. And then take the derivative of that is 1 plus, again, I'll have sine 3x stays the same in the denominator, and then I take the derivative of that, which is going to be 3 cosine 3x in the numerator, minus x plus 3, derivative of x plus 3 is 1, minus x minus 5, and then derivative of x minus 5 is 1. So now I have that I can multiply both sides by y and get that y prime is equal to 5 over x minus 23 plus 3 cosine. I'll just simplify this. This cosine over sine is cotangent. So I have 3 cotangent 3x minus 1 over x plus 3 minus 1 over x plus 5. And then I multiplied everything by y, which is this guy here. So I'll just go ahead and copy it from here. Times my original function there. And then that would be my final answer. That's the derivative of this disgusting monster. So yeah, I wanted to kind of outline next the general steps for what we're doing here with logarithmic differentiation. So the first thing we have is that y in general, or log diff, we have y given as a function f of x. And f of x we either can't or don't want to differentiate by usual means. So we instead do logarithmic differentiation. So the first thing we do is we take ln of both sides. And by doing that, it allows us to simplify something here on the right-hand side. So I'll have that this is ln of y, and this will be some simplified version of this. So I'll just put a star on it, ln f of x. So this would be the simplified version of this, simplified by log rules. So simplifying this by log rules, we get this new kind of version of it. Then I take the derivative of both sides, and I get that this is y prime over y, as always. And this is going to be the derivative of the simplified version of this, which is going to be much easier than doing, whatever I needed to do before. And then I just multiply both sides by y, and I get that I have this 2f dx. And then whatever our simplified version of ln of f of x is, we multiply it by what our original y was, which is f of x. So these are our general steps, right? We take ln, we simplify using log rules, then we differentiate, and then we multiply by y, and then we're done. So that's kind of what logarithmic differentiation is useful for and how to apply it. Thanks.